All right. Hello, everybody. I hope the symposium is going good for everybody and you're getting the most out of it. We have put so much time, energy, and effort for this event to happen. And I would like to thank Eda, Serkan, Kürşat ve Dicle a lot for their effort and hard work for this event. So today we have Mahir Dölek from Boğaziçi University. He's a fourth year double major in physics and mathematics. And Mahir has absolutely exceeded all of my expectations and read an entire book that we were studying over the 2 months. And today what he's going to talk about is probably only like 10-20% of what he actually studied. He prepared a really great talk, and I hope everybody enjoys it as much as I did. So Mahir, it's all you.
Thank you. My name is Mahir, as you guys. Today I will be talking about critical thresholds for epidemics on networks. First of all, I want to give you an outline of my presentation. My presentation will be in 5 parts. In the first part, I will talk about networks, what are they and how can we represent them in terms. And secondly, I will be talking about how to find important vertices that we want to focus on, because it will be an important question later on. Then we will have epidemic models. In epidemic models, I will talk about the general case first, where we assume like every pair intersects each other. Then I will be talking about some limitations that model can have. I will be introducing networks on the epidemic study, and so I will solve for critical thresholds on epidemic and give you some other information about how the spread of the epidemic happens. Finally, I will be giving you some simulations on how epidemic spreads and how should we vaccinate population in order to achieve a better solution for the to prevent the spread of the epidemic. To start my presentation, I want to give you first of all an example of a network to give you an idea. In network, we have 2 parts basically. One, nodes what we have, and nodes represent generally some sort of entities, and the edges between nodes represents some sort of relationship in the network. And in this network, we have a Charette club, and Charette club represents every node represents a people, a person, and the edge between 2 nodes represents a friendship relationship. And in general, epidemic models, we want to use some sort of friendship relationship, so it will be an important model for us, especially if we use this sort of connection. If we want to represent a network mathematically, we need 2 sets, as I said. One vertex set we need, we will denote it by V, and one edge set. And by specifying these 2 sets, we can just have a representation of a network, also known as graph. And in this talk, I will be using number of vertices and number of edges. M will represent number of vertices, and M will represent number of edges. Generally, if we want to use some sort of mathematical tool to represent a network, we use an adjacency matrix. Adjacency matrix is defined as follows, and I will use Aij to represent adjacency matrix. It will be 1. The entry of Ij will be 1 if there is an edge from vertex J to vertex I. And if there is no edge from vertex J to vertex I, it will be 0. I want to give you some examples of the adjacency matrices. In undirected graphs, we have following graph in here, and the adjacency matrix becomes like that. Since there are no sub loops in the graph, we have zeros on the diagonal entries. And since we have an undirected graph, we can go from J to I or I to J as we wish. So it will be a symmetric matrix as well. If we have a directed graph, it doesn't have to be symmetric necessarily. It doesn't have to be a triangular as shown in here, but it can be sometimes. It will generally be non-symmetric matrix, and it will be similar. And we have something called a weighted graph. In weighted graph, we will have weights rather than just 1 and 0 on the entries. This can represent some circumstances like, okay, in friendship relationship, for example, we can be close friends with some people and not so close friends with other people yet still know them. It can represent this, for example. And once we define the concept of a network or graph, we will be having a natural question. There are some vertices, but we want to know whether some vertices are more important than the other ones. And the answer is generally yes. What can we think of for the importance of the vertices. How can we determine that? The simplest explanation that comes to mind is to use just how many neighbors does a vertex have, and then think of it as an important quantity. So we will have degree centrality, which just represents how many neighbors a vertex has. It is represented by this formula. But this is not always a good formula, since sometimes we will have vertices with only few neighbors, but those neighbors are influential. For example, in a social network, if I know a lot of influential people, although I know some influential people, although I know just barely few people, I will be an important person still. We can have some sort of relationship, and to represent this, we introduce eigenvector centrality. K1 here is the leading eigenvector of the adjacency matrix, and this is generally calculated iteratively. It is an important quantity as well. But this quantity, this centrality measure sometimes fails as well. And especially in the directed case, it can give 0 for some vertices which we don't want. So we introduce yet another centrality measure. It will be xi, and this alpha and beta are just some constants, and we just calculate it like that. Beta gives some sort of like change in the measure that it will not make any vertex 0 base. Finally, we can think of another one, PageRank centrality. This you can think of a internet connection, for example, where vertices represent web pages and edges represent some link from that page to another one. And in this case, we will have like some sites that has too many links, but likely they are not important. Like not all of them are as important. So we divide this measure by just k out, which means the out degree of our vertex. So it just normalizes. And the name PageRank actually comes from a very interesting place. In Google, when we search something, we rank the pages by just this algorithm, using this algorithm, some sort of variation of this algorithm. And then we get the highest centrality measured ones at first, and then the others one as follows. Then we have different centrality measures. Closeness centrality is just the mean geodesic distance inverse. The mean geodesic distance is, I think you can like think of it as like how close are we to other vertices in about average. And we take the inverse because we want higher centrality measure to be like a positive thing, and there is no other reason. One final thing is between the centrality. It is about like how close are we to other like paths from one vertex to other. We take two paths, two vertices, find the shortest path between them, and then we check if we are in this path or not. If the vertex I is in this path, we just put NIST equals 1. And GST is just the number of geodesic paths. It's necessary because there can be multiple geodesic paths, and this just normalizes the equation. I know it's complicated, so I want to give you some sort of visualization to show how it works. In general, the different vertices here, there is a like high concentration of high centrality vertices here, there. But for concentrality, it changes. For closeness centrality, it goes to middle, and then it's very separated in between centrality. So different centrality measure gives us different idea about the network, and each vertex is very important. I want to move on to epidemic models then. First of all, I will divide the population into 3 different categories. First, susceptible, represented by S, infected, represented by I, and recovered, represented by R. The simplest model that we can think of is susceptible people become infected and stay infected. It will be called SI model and can be represented by this Markov chain. Then we can have infected people can recover from the disease and be fine with it, have an immunity to it, so they do not cause disease again. It will be represented by SIR model. Then we can have infected people become well, but they are still susceptible to this. They can cause the disease one more time, so it will be SIS model. And one final model that we can have, SIRS model, it will be. We can cause the disease, then recover from disease, but after a while we lose our immunity, just like in the case of COVID, and we go back to susceptible population as well. It will be represented by SIRS model. All models can represent different viruses or infections, so it is kind of related to biological nature of the infection that we see, which model we want to use. The dynamics of the model is represented by some constants. Beta is the rate of transmission. gamma is rate of recovery, and delta is the rate at we lose immunity. Beta is given there. It will be X and S represents some sort of relationship between infected people and susceptible people. Gamma represents basically how fast infected people recovered from disease, and there is delta at the SIRS model. It represents at which rate we lose our immunity to the disease. But these models assume all parts of the community interact with each other at the same rate. This is in general not true. For example, in the school, I do not know everyone. I know just some people and interact with them generally. So it's likely that I will cause the disease from them. So if we think of a friendship network, we can better model the epidemic that we have at hand. So I will be introducing networks to that. Now we had, if you remember, some sort of excess term. We know how that can translate to this one. S is the susceptible people, and we need the neighbors of ith vertex that are infected. We can represent it like that. Then we can use some manipulations to find this first equation on SI model, this equation, to be this one. And similarly, we can solve for the xi case, and it will be this equation. Now, once we reach here, we will see that we need some assumptions to solve this model at first stage, because we do not know the adjacency matrix. Here, Aij represents adjacency matrix, as you see here. And to make this assumption, we will assume that only few people are infected by the disease at first, which means xi is very small compared to 1. So we can just think of this term as 1. And once we think of this term as 1, this part just will be a very simple equation that you can see here. We can solve this equation very simply, but we will first write it in A's eigenbasis, because it will be important later on. And then we just manipulate the equation. We match the term with VR as coefficient. And then we just find an equation such that. Then we solve for x. The x is like that. There is a typo here, I think it should be VR. So we see that the highest contribution comes from leading eigenvector. And I want to remind you what was eigenvector centrality. It was defined like that. And if we go back one slide back, there is a term just very similar to this one. So actually, there is a case that can be made, which is a little bit long to argue, but the first leading eigenvector, the eigenvector centrality vertex is calculated this first in the population at the initial stages. Then we want to go to SIR model to see another different phenomena. And this phenomena, again, we solve for the general case, the initial case. At the initial case, we see this one. Now a different matrix is there, which can be represented as that. Again, it is easy to solve. I will not be solving it. And then we have some sort of relationship like that here. If this term has a negative derivative, then we see that disease that we have will be decreasing. So we will not be having an epidemic. There is a threshold, which we can see here. And if we are below this threshold, so it is a less than sign, then there won't be an epidemic. And this K1 here is the leading eigenvector, which is always positive because we have a theorem called Perron-Frobenius theorem, which applies to this case. So actually, we can find by just defining the terms, defining the gamma and beta parameters here, then we can find whether there will be an epidemic or not. Finally, I want to show you some of the simulations that we can make. I used a Python library called Ion and to make the simulations. First of all, I choose a very small beta to gamma ratio. It is 1/10, which is below the case. And I use no vaccination. On a graph generated by these conditions, which means there are 100 vertices, and there is only a 5% chance that there is a edge between any two selected vertices in this graph. And you can see that susceptible population is represented by green here, infected population represented by red, and the recovered population is represented by gray here. Now, since we have a very small beta to gamma ratio, we see that first of all, we have a lot of vertices that do not cut the disease at all at the end. About 80 of them do not cut the disease. and only some of them cause the disease. So we can say that there is no epidemic in this case, even though the vertex number is low, because this is below the critical value. Now I want to increase this number, which represents basically how fast people got to disease, represented by beta, and how fast people recover from this, represented by gamma, to 1. And if I increase this number to 1, we can see that the population now becomes a lot more like sick. A lot of vertices become sick at first, and then recover, of course. But now, if we look at the susceptible number, it is just 10, about 10 for the case that we have here. So if we increase the beta over gamma ratio to 1, we see that there is an epidemic and a lot of vertices become sick in this model. Now we talked about I talked about vaccination, but I do not. How can we vaccinate the population to prevent the spread of the disease? Is the next question that I want to answer. And to answer this question, I will be first of all choosing random vertices to vaccinate, and I will vaccinate 30 of them. And we can see that we have this sort of relationship where again there are about 10 people who are susceptible to disease at the end of the simulation. And this means that there is not a lot of change in the way that in the way of the epidemic. So a lot of people got sick, and which means the vaccination of 30 people are not as effective in this case. But if we were to use what we learned from the model that we have, which means that highest eigenvector centrality versus cause the disease first, then we can just vaccinate them, and we should have a better result, which I simulate here as well. In this case, the vertices with highest eigenvector centrality are vaccinated. And once we look at that, there are about 20 to 25 people who do not cause the disease, which is an increase of about 10 people, which shows that actually the model that we predict gives us a strategy for how we should do vaccination in the population. I want to briefly summarize my presentation. We talked about the epidemics on networks and how can we model them. We see that different vertices, different nodes have different centrality measures, and these centrality measures can select some nodes to be more important than others, and they change by changing the centrality measures. We see that different epidemic models can be used for different natures. For example, for chickenpox, we use a different one. For COVID, we use a different one. And we can get some idea about how the disease spread by just using networks. In both an SI-West and SIR models, we see that high eigenvector centrality nodes are more susceptible to catch the disease. And in SIR model, we also see that there is a critical threshold for the epidemic to happen. And if we are below the threshold, there is no epidemic. If we are above the threshold, there will be an epidemic most likely. And finally, we made some simulations using Python library. And on the simulations, we see that targeted vaccination of high eigenvector centrality nodes, as opposed to random vaccination, is a more successful strategy, as can be predicted from our model. Finally, I want to thank the RP Organization Committee for this opportunity to give for me to give this presentation in this symposium. I want to thank Ilgan for his mentorship throughout the program, and finally, I want to thank you for listening to the presentation.